If you've ever opened a research paper and thought, I want to understand this, but this is dense, then this podcast is for you. Every day, thousands of research papers are published. Most of them are rigorous, insightful, and almost impossible for non-specialists to read comfortably. But the ideas inside them shape medicine, technology, business, and society. Welcome to One Paper Orbit. We are a research paper podcast. Here we take peer-reviewed research and turn it into clear, structured conversations without adding speculation, without exaggeration, simply making the original work easier to understand. Today we are discussing a paper authored by Lothar Meisenbacher, Vitaly Werthel, Arthur Matvev, Alexei Grinin, Randolph Pohl, Theodore W. Hensch, and Thomas Udom, titled Subpart per Trillion Test of the Standard Model with Atomic Hydrogen, published on 11 February 2026 in Nature. This discussion is based on a paper published under the Creative Commons Attribution 4.0 license. The original authors retain credit for their work. This podcast provides an adapted explanation for educational purposes with full citation and license information provided in the description.
Well, it is incredibly exciting to be here for this one.
Yeah, welcome back to the deep dive, everyone. Today we have a literal puzzle for you. Imagine waking up one day and realizing the tape measure you've used your whole life to build, everything you own, has been subtly changing its size behind your back.
Which would be terrifying.
Right. You wouldn't just question the tape measure, you'd question the actual underlying geometry of reality. And that is essentially what happened to particle physicists starting in 2010 with what became known as the proton radius puzzle. We had two different ways to measure the proton, and they suddenly gave violently different answers.
Like physics breaking different.
Exactly. So what's our mission today?
Well, the mission of our deep dive today is to explore how a team of physicists finally put that puzzle to rest. We're going to look at how they fired highly specialized spectroscopy lasers at ultra-cold hydrogen to test the absolute limits of our current framework of the universe.
The standard model, right.
Yes, the standard model. And they managed to test it to an unprecedented 0.7 parts per trillion. I mean, it is just an absolute masterclass in taking experimental precision to the razor's edge of what quantum mechanics even allows.
Okay, let's unpack this. Because before we get into the lasers and the ultra-cold beams, we need to establish the stakes for you all listening. Measuring the physical size of the proton, the charge radius, isn't just trivia.
No, not at all. It's fundamentally tied to quantum electrodynamics, or QED. QED is it's basically the crown jewel of the standard model. Right. It's a relativistic quantum field theory describing how light and matter interact.
And hydrogen is the best way to test that.
Oh, absolutely. If you are going to test QED, atomic hydrogen is your ultimate theoretical testbed. Because of its structural simplicity, physicists can calculate its energy levels using bound-state QED perturbation theory to just astonishing accuracy. We're talking up to 13 significant digits.
Wow. But those theoretical calculations are mathematically anchored to a few constants, right? Most notably the Rydberg constant and, of course, the proton's charge radius.
Right. The size of the proton dictates these really subtle shifts in the electron's energy levels. And for decades, the physics community relied on a standard measurement for that radius. It was primarily derived from regular atomic hydrogen spectroscopy.
But then 2010 happened.
Yeah, in 2010, the Paul Scherrer Institute ran an experiment that, they swapped the electron and hydrogen for a muon.
And just to clarify, a muon is essentially a heavier cousin of the electron, right?
Spot on. The rationale there lies in the mass difference. A muon is about 200 times more massive than an electron. And in quantum mechanics, the Bohr radius of an orbit scales inversely with the reduced mass of the system.
So because it's heavier, it orbits way closer.
Exactly. Because the muon is so heavy, its wave function is incredibly tightly bound. It actually spends a significant fraction of its time literally inside the spatial distribution of the proton. This proximity magnifies the nuclear size effect on the energy levels by like 10,000 times.
Okay, so it's acting like a massive magnifying glass on the proton structure. That should have given us the most reliable number in history. But the result they got was tiny. It was significantly smaller than the established Codetta 2014 value.
Yeah, and it wasn't just a minor calibration quirk either. The muonic hydrogen result was more than 5 sigma off from the established atomic hydrogen value.
5 sigma? I mean, in high-energy physics, a 5 sigma discrepancy usually announces a completely new phenomenon, doesn't it?
It does. It suggests a less than 1 in a million probability that the result is just a statistical fluke.
That brings us back to the tape measure analogy. It's like paying a surveyor to laser measure your living room, only to be told the house is a foot smaller than the architectural blueprints say. You were basically left with three uncomfortable options.
Right. Either the old atomic hydrogen measurements were flawed, the new muonic measurements were flawed, or quantum electrodynamics itself is fundamentally incomplete.
Which is a huge deal.
It is. Because that third option implies a new, unknown physical force acting on muons that simply ignores electrons. That would be a violation of lepton universality.
So to figure out if QED was broken or if the old measurements were just wrong, researchers needed an experiment with terrifying precision. Which brings us to the methodology in this Nature paper. You can't just throw regular hydrogen in a glass tube and shine a flashlight at it.
Far from it. The researchers at the Max Planck Institute constructed a highly controlled environment. They generated a beam of cryogenic hydrogen atoms, cooling the atomic beam down to 4.8 Kelvin.
That is extremely cold.
Extremely. By reducing the thermal motion, they drastically minimized transit time broadening and second-order Doppler shifts. They prepped these cold atoms into the 2s metastable state. Then they fired a 410-nanometer spectroscopy laser at the beam.
To trigger what's called the 2s to 6p transition, right?
Yes. They're targeting the 2s to 6p fine structure transition, looking for the exact frequency of light that causes that quantum jump. And the precision scale here is really the defining factor.
How precise are we talking?
They're searching for the transition frequency to 1 part in 15,000 of the experimental line width. They're trying to pinpoint the absolute dead center of the resonance curve.
Okay, wait, I want to push back on that for a moment. If you're just shining a laser at an atom and waiting for it to glow, why is it so incredibly hard to get an exact number? What's actually getting in the way?
Well, the barrier is that at this subpart per trillion scale, the mere act of measurement violently alters the state of the atom. You are essentially colliding with ghostly quantum mechanics. That introduces the first major theoretical and physical hurdle the team faced, the light force shift.
Ah, because the laser light itself carries momentum. The photon transfer physically kicks the atom when it hits it.
Exactly. It delivers a momentum kick, and that alters the atom's trajectory and velocity. And velocity is the enemy of precision here because of the Doppler effect. If the atom is moving toward the laser, the frequency of the light appears blue-shifted in the atom's rest frame.
So how did they fix that?
To cancel out this first-order Doppler effect, the researchers utilized two counterpropagating laser beams, one firing forward along the beam path and one firing backward.
Oh, that makes sense. If the atom is moving toward one beam, it's simultaneously moving away from the other, so mathematically the opposing Doppler shifts just cancel out.
That solves the Doppler problem, yeah, but it inadvertently engineers a massive quantum problem.
Right.
Overlapping two identical counterpropagating laser beams creates a standing wave of light.
A standing wave.
Yeah, the interfering optical fields create a stationary periodic structure of intense optical potentials, basically bright and dark spots right in the vacuum.
Here's where it gets really interesting, you guys. We are so used to thinking of atoms as little billiard balls and light as a wave. In classical optics, if you shine a light wave through a physical solid grating, the light diffracts into an interference pattern. But in this experiment, those rules completely invert.
They absolutely swap. Because these hydrogen atoms are so cold, their thermal de Broglie wavelength is significantly stretched out. We can no longer treat them as classical particles with a defined position.
Right, they behave as quantum matter waves.
Exactly. This phenomenon is known as the Kapitsa-Dirac effect. As the hydrogen atoms travel through this standing wave of the 410-nanometer laser, they don't just absorb a photon at a discrete point in space.
Their wave function gets smeared out, right?
Yes, their wave function becomes partially delocalized over the optical standing wave. The atom is simultaneously traversing the bright spots and the dark spots, and its matter wave coherently scatters off the periodic potential of the light itself.
Okay, but that coherent scattering has to distort the energy of the transition they're trying to measure.
It does. It shifts the resonance significantly. It generates what the authors referred to as the light force shift, or LFS. And because the atoms are quantum mechanically delocalized, you simply cannot model this shift using classical mechanics.
Because a classical trajectory calculation just collapses in the face of wave-particle duality at this scale.
Precisely. You can't just plot the atom's path on a graph and subtract the kick.
So how do you calculate a shift when the object you're measuring is smeared across the very tool you're using to measure it?
The researchers had to deploy a sophisticated mathematical framework called a Wigner function. Think of a Wigner function as a quasi-probability distribution that operates in phase space.
Phase space, meaning it tracks both position and momentum at the same time.
Exactly. It is a unique tool because it allows physicists to simultaneously map the classical properties of the system, like the macroscopic motion of the atomic beam, while rigorously incorporating the quantum interference effects. Those are represented by regions of negative probability in the function.
Wow. So it bridges the classical and the quantum. It lets them plot the macroscopic movement of the hydrogen while also tracking the waviness of the atoms diffracting off the light.
Right. By quantizing the atomic motion exclusively along the axis of the standing waves and treating the other spatial directions classically, the Wigner function allowed the team to simulate the precise diffraction and scattering of these partially coherent matter waves.
And from that simulation.
From that, they could calculate the exact asymmetric distortion the light force shift was imposing on their transition frequency and meticulously subtract it from the data.
Calculating the quantum diffraction of an atom bouncing off a grating of light just to fix the calibration of your ruler is astonishing. But yes, as if atoms diffracting on light wasn't enough, they ran into a second quantum hurdle, didn't they?
They did. Getting the atom to the 6p energy level is only half the transaction. The atom returning to its ground state creates an entirely different class of noise.
Because exciting the atom to the 6p level is transient, the state is highly unstable.
Very unstable. It rapidly decays back down to lower energy levels, emitting fluorescence photons in the process. Those emitted photons are the critical signal the detectors capture to prove the transition actually occurred.
But the problem is, the decay isn't a single-lane highway. There are multiple potential decay paths from 6p down to 2s.
Multiple paths that lead to the exact same final quantum state, yes. And in quantum mechanics, if multiple indistinguishable paths exist for a process, the probability amplitudes of those paths interfere with one another. This is known as quantum interference, or QI.
So just like ripples on a pond, the probability waves of the different decay channels overlap. They can constructively amplify each other or destructively cancel each other out.
That's a great way to visualize it. This interference alters the spatial distribution of the emitted photons, which in turn distorts the shape of the observed resonance line.
It creates an asymmetry, right?
Exactly, a subtle asymmetry. Instead of a perfectly symmetrical bell curve for the transition frequency, one side gets pulled. This physically shifts the apparent center of the transition line that the detectors are trying to lock onto.
So the atom is effectively disguising its true transition frequency through the complex geometry of its own decay. Now, in previous experiments I've read about, resolving this usually involved building massive, purely theoretical mathematical models to estimate and subtract that asymmetry.
True, but for a subpart per trillion test, relying entirely on theoretical models to subtract a fundamentally quantum distortion leaves way too much room for systematic error. They needed a physical, experimental suppression of the interference.
And the elegant fix they came up with is just amazing.
It really is. They achieved it through an incredibly elegant application of geometry. They used a magic polarization angle.
I love this concept. How does physically rotating a piece of equipment cancel out quantum interference?
Well, what's fascinating here is how the quantum probability amplitudes manifest in physical space. The different decay paths from the 6p state represent different dipole radiation patterns.
Okay, so they emit light in different shapes.
Right. And the magnitude, and critically the sign positive or negative of the quantum interference distortion, depends directly on the angle at which you observe the emitted photon relative to the polarization axis of the laser light that excited the atom in the first place.
So the interference pattern is directional. If you place your detector at one angle, the transition frequency looks shifted higher. But if you move the detector to a different angle, the frequency looks shifted lower.
Exactly. The team realized that because the angular dependence of these interference terms involves specific mathematical functions, essentially Legendre polynomials, there exists a specific orientation where the positive interference terms and the negative interference terms sum to exactly 0.
And they calculated this magic angle to be 56.5 degrees.
Yes, they calculated it to 56.5 degrees.
So by physically rotating the linear polarization of their 410 nanometer spectroscopy laser to exactly 56.5 degrees relative to the axis of their detector cylinder, the quantum interference just vanishes.
It vanishes. They turned the polarization dial to 56.5 degrees, and they combined that precise geometry with massive detectors. Their detection setup covered over 20% of the total solid angle surrounding the interaction zone.
That's a huge detection area.
It is, and this massive detection volume essentially integrated over and averaged out any residual directional dependencies or tiny misalignments. By implementing this magic angle, they suppressed the quantum interference distortion so profoundly that the remaining frequency shift was reduced to a negligible fraction of a kilohertz.
The elegance of using macroscopic geometry to zero out a subatomic probability problem is just brilliant. So the Doppler shifts are canceled by the counterpropagating beams. The Kapitsa-Dirac scattering and light force shift are successfully modeled via Wigner phase space functions. And the quantum interference is completely bypassed by twisting the laser polarization to 56.5 degrees.
The noise is entirely stripped away.
The experimental state is pristine. So what was the transition frequency the universe finally revealed?
After recording and analyzing thousands of line scans over months of continuous measurement, extracting the Doppler-free transition frequency of the 2s to 6p fine structure centroid. The final number was 730,690,248,610.79 kilohertz.
I want to make sure the scale of that number lands for you guys. 730,690,248,610.79 kilohertz. And the uncertainty.
The uncertainty on that measurement is just 0.48 kilohertz.
That borders on science fiction. But the raw frequency is only the stepping stone, isn't it? We need to know what this uncovers regarding the proton radius puzzle.
Right, the ultimate payoff. They took that ultra-precise 2s6p frequency and combined it with the extraordinarily well-known 1s to 2s transition frequency. From that combination, they extracted the new proton charge radius.
Send the envelope, please.
The final calculation yielded 0.8406 with an uncertainty of 0.0015 femtometers.
0.8406 femtometers. How does that compare to the historical atomic measurements and the disruptive muonic measurement?
Well, this new atomic hydrogen result is 2.5 times more precise than the previous best test of its kind. And the verdict is definitive. It perfectly matches the 2010 muonic hydrogen measurement.
It matches. So the muons weren't experiencing some phantom fifth force of nature.
No phantom forces. The leptons behave universally. The old standard atomic hydrogen measurements were simply wrong.
The old CODATA 2014 value, which the entire physics community trusted as bedrock prior to the muonic experiment.
It was wrong by 5.5 sigma. The muonic measurement was accurate all along. The systematic errors were just hiding in the less precise atomic measurements of the past. This paper unequivocally proves it.
So what does this all mean? If you were listening to this on a commute or at your desk, what is the broader implication that these researchers spent years diffracting atoms on light just to confirm a number we strongly suspected was right from the muon data?
If we connect this to the bigger picture, it means the standard model of particle physics survives another day. By validating the muonic measurement using classical atomic hydrogen, they didn't merely measure a proton. They executed a stress test of the standard model itself to 0.7 parts per trillion.
That level of precision is staggering.
It is. They tested the complex bound state quantum electrodynamics corrections to 0.5 parts per million. It stands as the most precise test of its kind ever performed.
They basically demonstrated that the core mathematical framework we rely on to describe the interaction of light and matter holds together flawlessly all the way to the 13th decimal place.
Exactly. The perceived crisis in physics wasn't a crack in the foundation of reality. It was just a crack in the older, less sensitive rulers we were using. QED remains incredibly stubbornly predictive.
We've now mapped the charge radius of the proton to a fraction of a femtometer, confirming the standard model at scales that are almost incomprehensible to human intuition. But here is a final thought for you to mull over as we conclude today's analysis. The physics community is rarely satisfied with a closed case. Laboratories around the world are already designing colder atomic traps, more stable continuous wave lasers, and more sensitive detectors to push into the 14th and 15th decimal places.
Because there's always a deeper level to look at.
Right. Because if a true discrepancy, a real break in the standard model, is hiding in that next decimal place, it won't just be a miscalibrated laser. It will be the gateway to entirely new physics. Perhaps the signature of dark matter interactions or undiscovered weakly interacting bosons. The deeper we dive into the subatomic, the more the universe demands absolute perfection from our tools.
Beautifully said. It really is a thrilling time for physics.
This paper is published under a Creative Commons Attribution 4.0 license, and full credit is provided in the episode description. Thank you for listening to One Paper Orbit Hess, our research paper podcast. Our goal is to make peer-reviewed research accessible to everyone. If this episode was helpful, please share your thoughts and let us know which papers you'd like us to explore next. Thank you.